Let's say we have a continuous beam with both ends fixed and two internal rollers. The magnitude of uniform load on end span is twice the loading magnitude for internal span. On the other hand, the length of internal span is half of the end spans. We set the convention of internal moment next, where clockwise direction moment is considered positive. For each member, we calculate the stiffness based on modulus of elasticity, second moment of area, and span length. After calculation, we know the stiffness of internal member is twice of that for end spans. For each span, we need to determine distribution factor based on the boundary condition at both ends. At joint A, AB, which denotes the distribution of moment at node A to B is 0. This is because the fixed support can carry moment, and there is no need for it to distribute the applied moment elsewhere. Same goes to DC when we are looking into node D. At node B, two members are connected, namely BA and BC. The distribution factor for spans supported by internal roller equals to the ratio of individual member stiffness to total stiffness. As a result, we obtain distribution factor of 1/3 for BA and CD and 2/3 for BC and CB. Up next, we calculate the FEM in each member based on the loading condition using readily available formula. At the same time, we put negative sign to the end moment that acts in opposite direction with the established convention. To ease the moment distribution, we need to construct a table like this. Under each node, we first calculate the sum of moment acting on it. Then, this total moment is multiplied with the distribution factor for each connecting member. This process calculates how much moment is taken by each span under this loading condition. Finally, we need to change the sign of distributed moment, namely from positive to negative and vice versa. After the distribution among adjacent members is done, the moment is then carried over to opposite end of each member. For instance, moment distributed for member BA is carried over to member AB, and the amount of carryover moment is half of that for distributed moment. The process continues until the value of distributed moment closes to 0. The value of end moment for each span is calculated by summing the FEM, carryover and distributed moments under respective column. However, for this case where moment is expressed in fraction form, we can opt for exact solution by implementing geometric series. For instance, by observing the moments we need to add for AB, we found certain pattern. By excluding the FEM amounted -2/3 from the consideration, the remaining terms is a geometric series, where the initial value of the series is -7/72 and the common ratio is 1/3. Therefore, the exact solution for end moment AB is the sum of the series to infinity and add on the external term -2/3. By using this concept, the exact values of end moments can be calculated. Note that some calculation may involve two geometric series, and we need to identify each of their pattern and establish their own sum to infinity expression. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.